In this lecture, we are going to discuss QuickSort. QuickSort is similar to merge sort. It is another recursive sort, another divide and conquer method. First, let's look at the history for QuickSort. QuickSort, developed by Mr. C.A.R. Hall, 1962, works as follows. The algorithm selects an element called pivot in an array, divide the array into two parts such that all the elements in the first part are less than or equal to the pivot, and all the elements in the second part are greater than the pivot. Recursively apply the QuickSort algorithm to the first part and then the second part. Let's look at this chart. This is a conceptual idea of QuickSort. The implementation can be array or array list. So don't just limit yourself to array. Even though in the early days they are using array because of the limitation of memory and the programming language. Right here, if we pick 65 as a pivot, then we start it from the first element. If it is bigger, we start to throw it to the right side. If it is smaller, we throw it to the left side, trying to do that continuously. So we divided the array into two parts, one upper part, one lower part, and the pivot in the middle. Similarly, we pick another pivot, and then we throw the smaller on the left, continue to do that until it ends up with only one element, that's the end, and then return back to assemble back to a full sorted array or array list. Now let's look at the QuickSort in array format. We are using the pivot at the first location. Some algorithms pick the last one as the pivot. Let's focus on our format. Say the original array, we have a pivot at the leading location. So we pick that, throw everything smaller than it to the left, bigger than it to the right. And then so we pick the pivot of 5, move to here. And then we pick 4 as a pivot for the lower part, and we throw everything smaller than it to the left. And then we pick 0 as a pivot, we throw everything bigger to the right. And then we pick 2 as a pivot, throw smaller to the left, bigger to the right. And these are sorted. We have a 0, 1, 2, 3, 4, and then 5, similarly for the bigger part. Now let's look at the partition part for the first run of the QuickSort. We have a pivot, we have a low pointer and a high pointer, and we continue to travel. If the low pointer's element is smaller than pivot, then there is no problem. That means that the small one is the correct one. And for the higher one, we need to have a bigger one. If it is still bigger than 5, we continue to travel down the high until the low hit the bigger one and high hit the smaller one, then we do swap. After swap, we continue until you hit another bigger one on the low and the smaller one on the high, we swap. And then until the high and low crossover, we know that pivot should be in between there, and then we just swap the high with the pivot. Swap is the crossover point. When low and high crossover, the high index is pointing to the location that pivot should be, and then we swap the high location with the pivot. So now we finish the partition. On the left is smaller, on the right is bigger. We finish the first round. So the index got returned. Now let's look at the top-down partition and sort. At the top level for QuickSort, we get the array coming in, and the first element and the last element index, 2 index, and then we try to do partition for the array and the first element and the last element. First element for the low, last element for the high, both are index. And then it will return the pivot. Once it returns the pivot, we sort the first part, put in the first, that's the low for that coming array. And then we put the pivot index -1. That's the last one for the first part. And then we put the pivot index +1, that's the low for the second part, and last as the high for the second part. And then we do quick sorting. So right here, as you can see, this QuickSort algorithm is also a divide and conquer method. And when you branch out the sorting, it also coming in with about n element and branch out about half of the n if it is optimized. But in worst case, it will take longer time. Now let's look at the partition algorithm. When we get the array coming in, and the low and the high over here, so we set the low to be first plus 1, because we reserve the first one as the new pivot and high as the last one. And after that, we start to search for low location that had a bigger number. We keep increasing low index until it runs over, or if find a value that's bigger than the pivot. And similarly for the high index, we keep decreasing it until there's a crossover or the high index element is smaller or equal to pivot. If they don't cross over, then that two elements we need to swap. And we continue to do that until the crossover happens. Once the crossover happens, then we need to find the right pivot location. If high is greater than first, that means that the pivot is not the first location that the original pivot is. So we continue to decrease the high until the high is pointing to some location that's less than the pivot. Then that's the location that we would like to do swapping. So when we found the location, then we do swap and then return the high location. That's the previous new index. And if we quit doing that and we cannot find anyone, then we return first. So pivot doesn't move. It's just the first location. So in that case, we found a very worst case pivot at the first place. Now let's look at the analysis for the quicksort time. To partition an array of n elements, it takes n comparison and n move in the worst case. For example, if we have a pivot at the first location, and everything on the right need to be thrown to the left, then we need to compare and throw for n-1 times for the first one. And then if we pick another pivot, everything on the right is smaller than that, we need to throw again to the left. Then it's another n-2. So keep doing that. The worst case, we will have the n-squared algorithm. So this is similar to the insertion sort, selection sort, and bubble sort. Here is the analysis for the worst case time. And the best case time, if it is well balanced, we will end up with this. So this formula is similar to the merge sort. But because it is a best case time, so usually merge sort is performing better than the quicksort a little bit. But quicksort is easier to implement, especially when implemented by the array list or some list. The average case time will be the n log n time, will be similar to the merge sort. Now let's look at the program. Before we do that, we need to remember that quicksort is based on pick a pivot, so the bigger one to the right and the smaller one to the left. I use a short slogan of pivot and throw, pivot and throw. Now let's go to the program. The top level, we have shown it already. We partition and find the right pivot location, and the two parts, the smaller one being thrown to the left and the bigger one thrown to the right, and then we do quicksort for the smaller part, first half, and the bigger part, the second half. Now let's move to the partition. In the partition, we set the first location as the pivot value, and then we set first plus 1 as low, and the last to the high. And then if there is no crossover, we keep doing the following. First, we try to find some bigger value with the low, and we also try to find a smaller value with a high, and then we swap them. And we keep doing that until there is a crossover happen. When the crossover happen, we try to keep decreasing the high, because at that time, maybe the high pointer is pointing to something equal to the pivot or something, then we still need to do some swapping. Actually, this while loop, we try to find the new pivot location. If the pivot location we found it is bigger than that pivot location, then we do swapping. If not, we return the first element. Here is one example array. Let's run it. As you can see right here, it's well sorted. Thank you.